Okay, well, welcome everybody. Hopefully you can hear me. Welcome to our event of live streaming from Tortugas Mountain Observatory. Hopefully a good viewing of the great conjunction of Jupiter and Saturn. I'd like to start out by just some quick introductions of your hosts tonight. My name is John Holtzman. I'm a professor in the Department of Astronomy at New Mexico State University and also the department head down there. And I'm joined tonight by Dr. Nancy Chanover, who's also a professor in astronomy. How are you doing this afternoon, Nancy?
Hi, everybody. I'm doing great. I'm excited for us to see Jupiter and Saturn, hopefully.
Okay, and also hosting with us tonight is Zach Edwards, who is actually a staff member in the Department of Astronomy at New Mexico State, our lab observatory manager. How are you doing today, Zach?
I'm doing good. I'm excited for tonight, and I'd love to see the tornado.
All right, so this is great. So we're actually all coming to you from 3 different places. I'm actually sitting up in the observatory on Tortugas Mountain, just outside of Las Cruces, and Nancy and Zach are in their respective locations. So just to give you a brief idea of what we're hoping to do tonight, basically, I think we'd like to try to give you a little taste of what it's like to do some observing. Because I think a lot of astronomers find that to be a really fun and enjoyable thing to do. And we'll give you a little taste of it. This observatory allows us to have a little interesting perspective on the history of how observing used to be done and how it's done today. And maybe we'll give you a little taste of that. And so to do that, what we're going to do is we're going to start off in just a minute here with a quick walking tour of the observatory. Well, I'll be using my cell phone to walk around and show you a few things. That'll maybe be 10 or so minutes. Then I'll give you a short presentation about what conjunctions are, what the conjunction is, and how our telescope works. And probably sometime around 5 o'clock, it'll get sufficiently dark outside that we'll try to slew the telescope over towards Jupiter and Saturn, take a few pictures. Hopefully it won't be anticlimactic for you. It's just a few pictures we're going to take. And then we'll segue to Nancy, who is an expert on the giant planets, of which Jupiter and Saturn are 2. We'll give a short presentation on some of the science that she's involved with and that's happening at New Mexico State. And then we'll call it a wrap after that. So I'm going to start off now by doing a little walking tour. So I have to transition to my cell phone. So I'm going to do that here if I can. Great. So I'm walking out of our little control room, and as astronomers, the first thing we do when we come to the telescope is to ensure good seeing conditions. We want to make sure that the temperature on the inside of the dome is about the same as the outside temperature. So what we're going to do first is we're going to open up the dome. So I'm going to take you up this set of steep stairs. Hopefully it won't be too disorienting for you. Up from underneath the observatory, up onto the observatory floor. Turn on some lights here, which hopefully I'll remember to turn off. This is our observatory floor. And there's actually the telescope that we're going to be using tonight. I'll tell you a little bit more about that in a second. But we're in a big dome. I'm inside a big dome here, and what we're looking at there are 2 big double doors, which I'm going to try to open. Okay, so here we go.
Like we're there.
What do you think, Nancy? How does the weather look outside?
It's a little cloudy, but I think we might be able to push through.
I see some blue. We'll go outside here in a second and take a closer look. So those are the 2 dorms, and the whole dome can turn all the way around the building so we can point in any direction we want. Okay, so let me take you downstairs now. Oh, yeah, actually, there goes the dome rotating around to where the telescope is pointing. All right, coming back downstairs. I'm going to take you outside so we can see the lovely location that we're in. Here we are, broadcasting live. A few visitors to the mountain here.
Looks like we might have a nice sunset. And here we are looking out west from Tortugas Mountain, down into the Rio Grande Valley, the city of Las Cruces in front of us. The river runs down the far side of the valley, and a lot of agriculture in the valley. This is a wonderful place to come up to kind of get a perspective on where we live here. You can see the natural environment. The Rio Grande Valley is a big geologic rift valley. It's actually a very interesting place geologically. There's some interesting geology of the Tortugas Mountain that we're on right now. You get some interesting perspective on the human impact of the landscape and development and agriculture here. Lots of things that you could see. It's a great place to come up. If you live in Las Cruces and you haven't been up here, strongly encourage you to take a trip. Let's see, there's a cultural site up here, a shrine to the Virgin of Guadalupe. There's a tower, the KRWG radio tower, and over towards the west mountains to the east of Las Cruces. And this is where we're at. You can see my long shadow, this one. And then back to our observatory. This is the building we're in, the Tortugas Mountain Observatory. And there's the big dome with the double doors that we just opened. All right, so let me walk you back inside. This observatory was built in the late 1960s. And at that time, all the observing was done by people coming up to the observatory every night. And there had to be someone here, and there was no computer control. Things were all just done by an observer doing things by hand, and wasn't always clear, and there wasn't always necessarily an object to look at. So there was a building to support the observers to come up with. So coming in here, this was sort of the living quarters, an office space. I kind of like this here, actually back in this back corner here, there's Nancy was a student before she became a professor there, and she had the opportunity to appear and do some observing. So anything you could tell us about hanging out in this room? That's an old black and white TV. What do you remember, Nancy?
I remember watching the black and white TV when it was cloudy, taking naps, waiting for the skies to clear. And I remember there were often peppermint patties left in the refrigerator for me from the staff observer, Scott Merrill.
So here, hanging on the wall or on this table are some of the pictures that were taken in some of those early days of the planets. I don't know if anyone recognizes that one. Probably you do. Hopefully we'll see some stuff, maybe not quite looking quite like this, not to have your hopes up too much. There's the refrigerator where the peppermint patties were kept. So during the 60s and 70s when the observatory was built, it was before the age of digital cameras. So all of the imaging was done back then photographically. And the way that astronomers did the photography on telescopes is the emulsion, the photographic emulsion was laid on glass plates. And the process of observing would be going up to the observing floor, going into a dark room, putting in a glass plate in a plate holder, going up to the observing floor, bolting it on the back of a telescope, opening the shutter, maybe staring down an eyepiece to kind of keep the telescope tracking right on the same place in the sky, finishing your exposure, coming back down, and bringing the plate into a dark room. This is a dark room in the observatory, and doing the chemical processing that turned that photographic film into images which were measured. So this observatory is equipped with a dark room. This is no longer used anymore because now we're in the age of digital imaging. So that's that dark room. And let me just take you once more upstairs to finish up the tour. I guess I should have mentioned at the beginning that if you have any questions about anything, put them in the chat window to Zach Edwards, and we'll periodically turn to him to see if there have been any questions. Actually, Zach, have there been any questions?
Not yet, John. I just sent a reminder, so hopefully we get a few questions in.
Okay, I'll try to remember to break out to Zach to ask about that. So here's the back of the telescope. We're now looking out the slit. And so the way this telescope works, telescopes are measured in size by the diameter of their mirror because, as I'll talk about in a little bit, telescopes to astronomers are basically light buckets. They're buckets that collect a lot of light because most astronomical objects are faint. We have a hard time collecting enough light from them. The planets we're looking at today are an exception. They're pretty bright, so we actually don't need a telescope like this. The diameter of this telescope is 24 inches. Which may look big here, but it's actually small compared to lots of other telescopes. And the way the light works in this telescope is it comes in from the sky down the tube of the telescope, hits a mirror at the back of the telescope, which reflects light back up towards the front. And there's a mirror at the front, which reflects light out the side. And that thing you see hanging off the side is our digital camera. And that's what we'll be taking pictures with in just a little bit. So this observatory, like I said, started out doing photographic work, but it was actually a pioneering observatory in starting some of the first digital detector work over here. A big orange can. Inside that orange can down at the bottom that was bolted on the back of the telescope is one of the first digital detectors that was used for astronomy, a detector package that was developed at the Jet Propulsion Lab in California. And this one's pretty interesting to me because it turns out this was a prototype detector for some detectors that later flew in the first camera that was flown on the Hubble Space Telescope, which I had the opportunity to be involved with. And so that's kind of a cool connection. Another cool personal connection, both for me and Nancy, it turns out this telescope, a 24-inch Bowler and Chivens reflecting telescope, was actually the same telescope that my undergraduate institution had at their campus and that Nancy's undergraduate institution had at their campus. So I think when both of us got here, we kind of found an old friend at the telescope. And I spent many nights in my senior year, every single clear night in my single year, I spent behind a telescope like this one, but it was in Connecticut, so there weren't that many clear nights. Any stories from you, Nancy, on that?
Not too different. Mine was in Massachusetts, so not a lot of clear nights, but a lot of cold nights when we were stuck in the dome making our observations.
Okay, that concludes our tour. I'm going to come back now. We've renovated the telescope and it's actually controlled digitally through a computer, but you guys probably have all seen computers before.
And I did get one question. I got quite a few good questions, but someone asked, why does the temperature inside the dome have to be the same as the surrounding outside?
And that's because if they're very different, that causes a lot of turbulence in the atmosphere, just like you see the shimmering above the road on a hot summer day. And that shimmering in the atmosphere degrades the quality of the images that we can obtain. So ideally, we like the environment in the dome to be the same as the environment outside the dome, provided that it's clear.
Okay, so just a few things to walk through here. I already gave you some of the history of the telescope that was built in the late 1960s. And the main reason this telescope was constructed, and Nancy will talk about this a little bit later, was actually to study the planets. That was still in the kind of the golden age of the very first flybys. And this telescope was built largely to do some monitoring of the planets. That was in the age of the first flybys, the Pioneer missions, and then the Voyager missions, which were the first really close-up flybys of some of the outer planets. And it was used mostly for that work up through the mid-1990s. And at that point, pretty much use of this telescope stopped. And that was the time that coincided with the construction of the Apache Point Observatory, which is another observatory that New Mexico State is associated with, a much larger telescope built up in the Sacramento Mountains, south of Cloudcroft. It got a little bit more usage about a decade later, and something that Nancy was involved with. Do you want to quickly tell us what that was about, this L-Cross mission, Nancy?
Sure, that was a mission that NASA had planned intentionally to crash something near the lunar South Pole, so in a cratered region near the moon's South Pole, looking for water ice. And so the idea was that they were going to intentionally crash something, a bunch of debris would be lofted up above the moon's surface, and we would be able to measure it both from a follow-on spacecraft and from Earth. So we had several observatories in New Mexico, including Tortugas Mt Observatory, that were used to try to detect the debris plume, and we were successful.
But unfortunately not from this telescope, right?
No, we were successful from Apache Point Observatory.
Oh, well, good try.
Okay, it was a good effort.
Okay. The telescope has kind of gotten a second life in the last decade. About 10 years ago, we started a collaboration with a professional amateur society called the American Association of Variable Star Observers. Turned out the director of that group at that time was a friend of mine, someone who I'd worked with previously, and he had the idea. He grew up in Las Cruces and had the idea of trying to rejuvenate this for some of their members, and we entered into a mutually beneficial agreement. And we worked with a bunch of NMSU engineering students to come up and pull out all the analog motors and put in some digital motors and make the whole thing computer controlled. The dome used to be opened by a crank. You saw now it was just opened by a button. Maybe it used to be a little more romantic, but now it can be done remotely. And we're trying to have this telescope used for some of their research. They have members from around the world, and we're hoping to get it involved in a little bit of undergraduate research. And we're hoping to start a set of regular outreach programs like this one. We think it's a great observatory to do outreach with because pretty much everyone in Las Cruces is familiar with it, because you can see it pretty much from everywhere. And there are ever increasing numbers of people coming up Tortugas Mountain. A little over 10 years ago, the Bureau of Land Management, New Mexico State, entered into an agreement to operate the site as a recreation site. NMSU owns some of the land, BLM owns some of the land, and there's a few parking areas set up and a network of trails. And I like to hike up here a lot. In fact, I hiked up here today. I'm gonna have to hike back down in the dark. It's a really great place to come visit. So I think it's good to associate people with doing science. And here's just a slide with a montage of a few important people that were associated with this observatory. Many people may have heard of Clyde Tombaugh, the discoverer of Pluto, who didn't discover it here. He discovered it in Arizona, but he moved to New Mexico and was one of the founding members of the New Mexico State Astronomy Department and probably responsible for raising some of the money for this telescope. This person here's name is Brad Smith, and there he is at an older age. He was the first PhD coming out of New Mexico State in astronomy. And Brad apparently was fundamental in working with the design and construction of this telescope. He actually went on to be a principal investigator of one of the imaging teams on the Voyager missions and had a long career in planetary science. Rita Beebe, there, and a little older there, took over the operation of this observatory sometime in the mid-70s after Brad left. She was given a faculty position here. Fantastic catch that has paid off multitude of times. Actually, I should let Nancy say something. Rita was Nancy's advisor. Any quick word you want to say about Rita, Nancy?
I would just in the context of a Tortugas Mountain Observatory, she was really committed to making sure that our end of the bargain, NMSU's end of the bargain, which is to provide long-term monitoring of the planets, was fulfilled. And so we had a lot of opportunities to do that, and the data, have been used by lots of investigators over the years. She was a phenomenal advisor to work with, and she continues to teach me things to this day.
Yes, Rita's still active, and in fact, she may be lurking on this call. Hi, Rita. And then the fourth person I want to mention is Scott Murrell, who is a person a lot of people associate with this observatory. Scott was one of the main observers here. He was hired as an observer, and he was up here many nights just doing the observing. So there he is at the telescope. Scott passed away a number of years ago, but I did have the opportunity to come up here with him at some point, and he had some great stories to tell about the place. And I think the story is that Scott is the one who taught Nancy how to drive a four-wheel drive to get up this mountain. Is that right, Nancy?
That's right. Yes, that's right.
Okay, so there's a few people associated with it. Another exciting thing that we've just completed this year is an exterior renovation project. Finally, I thought we'd done enough getting the inside working in operation, but with the outside of this building was an embarrassment, and you could see what it looked like just a few months ago. And about a year ago, we did a fundraising campaign and raised enough money when matched with some building restoration funds from New Mexico State to redo the exterior. And so that's what it used to look like, and that's what it's looking like now. You saw a little picture from it outside. So we're proud of this. We think it's a location that Las Cruces and New Mexico State can be proud of, and we would like to share it with the community like we're doing tonight. Okay, so let's talk a little bit about conjunctions, which is what we're here to see us tonight. So what is a conjunction? A conjunction, the real idea is really simple. It's when two astronomical objects, usually two planets, come together to a very close separation in the sky. And here's a little diagram of the conjunction of Saturn and Jupiter this year. They were far apart in October, and since then they've been getting closer and closer and closer until today. They're very close to one another. They're not exactly on top of one another, and for those of you who are hoping to see a picture with two planets touching each other, we're not going to see that, but they're very close to one another. And so that's really what a conjunction is, when two planets appear in the same direction when seen from Earth. And why does that only happen periodically? So here's a little symbol of the solar system. Most people know that the planets all go in orbit around the sun. Here's a diagram of the planets. And what you may or may not know is that the planets go around at different speeds. The inner planets travel around faster than the outer planets. Let me speed this up a little bit. And maybe we'll zoom back out to see Jupiter and Saturn. And so you can see that Jupiter and Saturn are not going around at the same rate. If I speed it up a little bit more, it means that sometimes, whoops, there's Saturn went off the top of the screen. There we go. See, Jupiter is going to pass Saturn. There it goes, passing Saturn. And I'll speed it up a little bit more. And there it's going to go around and pass it again. And I'll try to stop it when it passes it. And if I, whoops, I missed stopping it. I'll wait one more time. All right, if I stop it there, then if you're on the Earth and you look in that direction, you see them both in the same line. And that's what a conjunction is, okay? And the planets go around at different speeds, so they're not always in the same direction. They're changing from different times. And so it's important to remember when they are close to one another, they appear in the same direction, but they're not actually at the same distance from each other. Okay, they're very far apart from each other in actual space. They just appear in the same direction when viewed from Earth. And that's what we're going to be looking at tonight. Jupiter and Saturn will be close to one another. It'll be fun for you to go out after this presentation is over and actually try to see them with your eyes. If you have good eyesight, you'll actually should be able to tell that they're not quite in the same place. If you have lousy eyesight like me, they kind of look blurred together into one. So here's the configuration that we see today. Jupiter and Saturn in about a line. There's Mercury, Venus, Earth. So Earth, Jupiter, and Saturn are all in about a line. Not too far away from the sun. We're seeing it low in the southwest just after sunset. So although it looks like they're in a direct line, we have to remember that space is three-dimensional. And if we were to take this picture of the solar system and tilt it over to its side, you get something that looks like this. And you see that the solar system is actually an incredibly flat thing. And we think we understand that from the nature of how the solar system was formed. But although it's very flat, it's not perfectly flat. So Jupiter and Saturn, one might be a little bit higher or a little bit lower than the other one. And in this picture, the dots are much too large for the actual size of the planets, given their separation here. So you can't really see it here, but it basically means when these things line up, they still don't lie exactly on top of one another. One is above and one can be below a little bit. Talk a little bit more about that in a second. Another interesting thing about today's conjunction is it happens to fall on the winter solstice, which is the first day of winter, the shortest daylight hours of the year. And that actually is just a coincidence. You could have a conjunction that could happen at any time of year, and this one just happened to happen on the winter solstice. So why is this conjunction a special conjunction? Well, it turns out that Jupiter goes around the sun once every 12 years or so, and Saturn goes around the sun once every 29 years or so. And if you put those two things together and do a little bit of math, what you find out that the conjunctions occur once every 20 years or so. So 20 years, it's sort of unusual, but not that rare. You get to see a lot of 20-year events. But because of the up and down part, that thickness of the solar system, every 20 years, they're not always the same distance apart. And what this figure is showing here, it's kind of an interesting figure. It's showing how far apart Jupiter and Saturn are at each one of those 20-year conjunctions. And you can't quite tell from this figure, but it kind of goes from one. This is from the year 0 up to the year 2000 or the year 2020. And every 20 years, it alternates from one of these things to the next one down here, to the next one down here, then up to the top one, down to the middle one, down to the bottom one, top one, middle one, bottom one. And there's lots of cycles inside of cycles here. On top of that 20-year cycle, there's a 60-year cycle, which is when the planets come about to the same part in the sky. And on top of that, there's something like a 400-year cycle, which are when things get close to this zero line, that's when the conjunctions are very close to one another. If they were exactly at zero, the planets would actually lie on top of one another. And you could see here in 2020, we're close to zero. We're not exactly at zero, but we're closer than most of the conjunctions are. And the last time that we had a conjunction where the planets were this close was about 1623, just about 400 years ago. We'll have another one in just a few decades that's about the same distance as this one, and then it'll be another 400 years or so until we see a next one. So that's what's kind of interesting. And really, this coming together of the planets to a fraction, about 1/10 of a degree, makes this event actually a special event for telescopes. Because if you're looking with your naked eye, any of these 20-year conjunctions, Jupiter and Saturn, are going to be pretty close. But with big telescopes, it turns out we can't image very large pieces of the sky. So there are not very many telescopes in the world that can actually image something that's a degree apart. So at most conjunctions, if we take a picture, we'd see Jupiter, or we could point, we could see Saturn. But at this distance apart today, we're actually going to be able to see Jupiter and Saturn in a single picture. Again, they won't be overlapping each other, but we'll see them in a single picture. And that's really what makes this special. It's special to see from a telescope. Okay, so whoops, sorry about that. So just a tiny little bit about how we're going to make these observations. We're making this observation using a telescope. This is a diagram of how our telescope works. I described it upstairs. The light comes down from the sky, hits a mirror, bounces up, hits a flat mirror that sends the light out to the side, and that's where we have a digital camera mounted. Although I don't know how many people are familiar with looking at telescopes, although that telescope may have looked large, as far as research telescopes go, that's a very, very small telescope. And in fact, that's why we stopped using it in favor of the Apache Point 3.5 meter telescope. Telescopes are measured by their diameter. This one is a 24-inch. And here's a diagram of some of the largest telescopes in the, on the Earth today, just to kind of get a feeling for where astronomers are at in terms of how big telescopes they use. So a 24-inch telescope doesn't even make it onto this chart. This blue dot here is a 40-inch telescope. So our telescope is a circle a little bit smaller than that. This blue circle up here I just drew in is about the size of our 3.5 meter telescope up at Apache Point, so considerably larger. But even that is now getting to be small compared to the largest telescopes in the world today, like the Hobby Elberly telescope, which is in West Texas. The South African Large Telescope in South Africa. There's 2 telescopes in Hawaii that are, oh, there they are, the Keck telescopes. Not really showing a good picture here. Some US National Observatory telescopes in Hawaii, and there's a couple telescopes in Hawaii. They get very large, and these telescopes are not built today. These are the telescopes of the future, truly gargantuan things compared to the size of the telescope that we're using today, or even the size of our telescope at Apache Point. And just to give you a feeling for how big people are thinking and how big they plan to big telescopes, down here is to scale the size of a basketball court and a tennis court, to give you a feeling for how big these things are. I should break out to Zach to see if there's been any questions from the audience. Zach?
Yes, I actually got a good question. I've gotten quite a few good questions, but I liked this one. How can we have data from 1 CE and thousands of years ago? How did we get that data from the graph you showed of Saturn and Jupiter's positions?
So those were not measured positions. What they are is they're calculated positions, because we actually think we understand why the planets go around the sun very well. They go around because of the force of gravity, and gravity is something we understand very well, and we're able to kind of run the current positions of the planets back in time and forward in time. Interestingly, however, it's an interesting question. Although we can do that for a few thousand years, it's hard to do for a much longer time, because gravity, although it's a simple idea that mostly the planets get pulled by the sun, they also get pulled ever so subtly by each other and other bodies in the solar system. And it's actually very hard to calculate the exact positions of things very far into the future. Any other questions you want to throw at me?
I do have a couple more. I'll lump them together. Why is the telescope so high on the top of a mountain, and why are we so concerned about clouds in the sky tonight? So that is, why are dark skies important, and why is a telescope being on a mountain so important?
Nancy, you want to take that one?
Sure. So in general, we want telescopes to be located at high altitudes, relatively speaking, so that they can be, in some cases, we want to be above a portion of as much of the Earth's atmosphere as we can be, because the atmosphere causes turbulence. For certain kinds of observations, we want to be above the Earth's atmosphere because the water vapor in the Earth's atmosphere can interfere with our observations. And so high altitude in general is often equated with being drier. And so those tend to be good locations. They also, we also like to be at a high altitude so that in some cases we can be above the clouds. That's not the case for Tortugas Mt Observatory, but some of the very highest observatories in the world are in fact above much of the Earth's weather layer. So the clouds, at least in the kind of light that we're going to be looking at using tonight, clouds cause problems because they block the light from the objects we're interested in. So if we want to be able to observe super faint things, which again, tonight's planets are not super faint, we really need to have a clear sky, dark sky, with very little interference from clouds or the Earth's atmosphere.
All right, thank you for that. Yeah, most astronomical objects are faint, and everything we can do to maximize our ability to see them is why we put telescopes where we do. So just a brief introduction to the way we're going to take pictures in just a few minutes here. We're getting close. We're going to be using this digital camera mounted on the side of the telescope. And what a digital camera is it's broken up inside on a detector to lots of little squares. And basically in each one of these squares, which represents a different location in the sky, a digital detector just records how much light hits that. And it basically counts what we call photons, the little packets of light that come from the sky. And so basically a digital image is just an array of numbers that represent how much light hit that location. And so this image here, which isn't a picture of much, is represented by this array of numbers here. And you can kind of see this dark place, that's the low number. This bright place, that's this high number. This dark place, that's this low number, 51. And so the detector spits out this big set of numbers, and then the computer takes those numbers and said, hey, wherever there was a low number of photons, I'm going to make it look dark. And wherever there was a high number of photons, I'm going to make it look bright. And that's the images that we're going to see today. But the detector that we use actually has the ability to observe a much bigger range from bright things to faint things than our screen is able to display. So when we take our pictures here in a couple minutes, you're going to see that I'm going to have to do some adjusting of the brightness and contrast of the image, something that may be familiar to those of you who had television sets long ago with brightness and contrast buttons. We'll be doing the same sort of thing to turn our digital images. And we'll see that a single picture, we can tune the brightness and contrast to see different parts of the image in greater detail. And finally, what are we looking at? We're looking at light. Light is the fundamental thing that astronomers use. And as you may know, there's several different types of light or flavors of light. What our eye sees as different colors of light. And in fact, all these different colors of light are themselves only a smaller part of what we call the electromagnetic spectrum that extends to other kinds of light that our eyes are not sensitive. Ultraviolet light on this side, infrared light and radio light, those are all different kinds of light. But our detector upstairs today is going to look at visible light, and that's why we care about clouds, because visible light doesn't come through clouds. So if we were observing in the radio, clouds wouldn't bother us, but observing in the visible, clouds do bother us. Our detectors don't have the ability to distinguish what color light they're seeing. So if astronomers want to study the colors, they often use filters, and this is a diagram of some of the common filters that are used in astronomy. So if we want to study what the red light is from an object, we put a piece of red colored glass in front of it, and we take an image, and that's what the object looks like in red light. If we want to know what blue light is coming from it, we take a piece of blue colored glass, put that in front of the camera, take a picture, and that's what the object is emitting in blue light. And if we wanted to make a color picture, we would take a picture in several different filters and then merge them together digitally to make a color picture. We're not going to be doing that tonight, so the pictures you're going to see are going to be black and white. So I'm just trying to get the expectations straight. And in fact, since the Jupiter and Saturn are so bright compared to all other astronomical objects, it turns out these filters, which let in fairly wide range of different colors of light, they're too much for our detector. They're going to overwhelm our detector. So we're actually using a very narrow filter that's just looking at one little sliver, one little type of red light. And that's the filter we're going to be using to look at Jupiter and Saturn. So let's go observing. Any questions on that, Zach, that we should do before we get this started?
I do have one question. Someone, when we were talking about a mountain, asked, why couldn't we put this observatory on Oregon Mountain since it's a bit higher? Why did we decide Tortugas Mountain?
Well, I was only a little baby when this was built, so I can't tell you. But I have been up in the Oregon Mountains a lot, and it would be a pretty rough place to build an observatory. And actually, I'm glad there's not an observatory up there. It's a wild, special place. But access, you know, when people go around building observatories, a lot of things, the conditions, the amount of light there, the quality, the turbulence in the atmosphere, but also the accessibility of the site, because observatories are big machines in big buildings, and there's a significant expense associated with the construction of them. And if you have to make new roads to get to the things, then that adds to the expense. And so it's a balance between a bunch of things. So Tortugas Mountain, I think, was really probably a spectacular location in the 1960s. As you can tell from this picture, which is a beautiful picture, but not really from the point of view of an astronomer, because of all these lights. Astronomers don't like to see that next to their observatories. And we have some dark skies ordinances in Las Cruces, but I think we could do a better job with that. But first looking at things like Jupiter and Saturn, there's no problem. Other quick question?
I think someone just asked the same question as you were explaining about light pollution. So how much does this light pollution in Las Cruces affect us here on TML?
Well, if we were doing dark sky research, it would affect us quite a bit. But that's not, I think, the main role or function of this telescope anymore. As you saw from the previous slide, this is a small telescope compared to even the research telescopes that NMSU has access to. So, there are some really interesting, bright things. One of our faculty members who's on this call, Eric Nielsen, studies planets around other stars, something that I think Nancy will mention. And actually, there's been a resurgence in the use of small telescope for studying what's called transits, when planets around other stars pass in front of their stars, and you can actually measure even with a small telescope a slight dimming of light. So we may try to get involved in that research. We haven't done that yet from Tortugas Mountain, but it's something that we probably could do without worrying about light pollution. Okay, so here I'm going to introduce you to our telescope control system that we're going to use. So just a quick little guide here. This is all computer controlled. We have a weather station outside that's telling us that it's clear and calm and still a little bit light out, but I think dark enough to observe Jupiter and Saturn. Down here we have our control of our camera that we'll be using to take pictures, and we'll see the images appear here, and I'll make that screen a little bit bigger. Up here we have a little focuser. Hopefully we won't be too far out of focus, but if we are, I might have to take a little digression and get us focused a little bit. And then finally here, the control panel where we're going to control where the telescope is pointed. So what I'm going to do without further ado is I'm going to tell the telescope to point to Jupiter. So you used to have to look these things up in coordinates, but now you just have a little menu that says go to Jupiter. Pretty easy. Let me close this one up. Go to Jupiter. And what I can also pull up is we have a web camera upstairs, which you can actually see the telescope moving, and the dome moved a little bit. So the telescope is actually pointed almost right back at where the web camera is, so we don't get a great view of it. So I think maybe we're about there. And all right, this is the moment of truth, guys. We're going to start off by taking exposure through our narrow filter. And we'll take an exposure. It's very bright, so we're just going to take an exposure about half a second, and we will see what we see. So it just opened the shutter for half a second, and now that digital detector is kind of reading out all those numbers and turning them into an image that looks like on the sky. And let me make this a little bit bigger. Steer around just a little bit. Oh. All right, so I don't know if you guys know what we're seeing exactly. I'm trying to do a little bit better, but now I'm going to take my little, this is the window that does the brightness and contrast. And things are still pretty bright out there. The sky is pretty bright. We'll be doing a little bit better as the sky gets a little darker, but let me try to adjust this contrast just a little bit. And now you kind of have a feeling for what you're seeing. This is it, guys, the great conjunction of Jupiter, no, that's not Jupiter, that's Saturn, and Jupiter. So let you admire that. But you see, it's hard to see very much detail. And so let's see, I think we might have to wait for it to get, well, maybe we can try a little bit different exposure. Let's just try this. Try just a touch shorter exposure to see if we can get something nice on Jupiter. Oh, very good. Okay, I need my little contrast window again. There it is. Actually, let's try something. While we're waiting for it to get just a little bit darker, let's try to take a little bit more close-ups of those planets. I'm going to adjust my brightness and contrast here, maybe. Great. And so there you can see an okay picture of Jupiter. Nancy, you want to tell us a little bit about what we're seeing there?
Sure. So you're seeing a series of white and darker colored, they're sort of orangey brown, if this were a color image, bands of clouds on Jupiter. Those are primarily oriented in the east-west direction. And so Jupiter's got these nice stripes that helps us figure out where the North Pole is, because they're perpendicular to those horizontal bands. But yeah, the bright clouds are regions where the atmosphere is rising, and the darker regions are locations where the clouds are subsiding.
So if this seems anticlimactic to any of you, we're kind of living in a jaded era, because we have these fantastic pictures from telescopes up in space, which are able to see much sharper detail because they're not blurred out by the effects of the Earth's atmosphere. Nancy's going to show a couple of those pictures later on, but this is what you see from a typical ground-based telescope. Some people can do better than this, and if we did a careful job of focusing and waited for a super nice night, maybe for it to cool off a little bit outside, we could see some more detail. But let's go back and take a full image one, and then try to do the same thing for Saturn.
John, while y'all are doing that, we have some people asking that if they were to go out right now and look for Jupiter and Saturn, where would they have to look?
So you would need to look in the southwest part of the sky. So over sort of towards where the sun just set, but a little bit to the left of that and up a little bit. And it might just, it's a little bit hard to see right now. It's probably still a little bit too light out. But in just a few minutes, that would be the place to go to look for it. And I would strongly recommend that you do that. That'd be great. Oops, I forgot to turn that off. Okay, so we're going to take one of our big pictures again to see our conjunction. Can't see this conjunction too many times, but every picture looks about the same. Again, I'll adjust my brightness and contrast because we have a digital image. And there we have Jupiter and Saturn again. So you can see, if I want to try to bring out the contrast, well, I can't even bring out the contrast in Jupiter right now. So let's try Saturn. Let's see if we can get a good close-up of Saturn. So I'll do that. And we can up the exposure just a little bit. Let's see what we can get for Saturn. Saturn is probably, in my opinion, one of the most spectacular things you can look at through a little telescope. It's just, the first time I saw Saturn, I was looking at it through an eyepiece. I was like, no, that's not real. That's just like some little sticker that's been glued on the back end. But telescope doesn't work like that. There is no little sticker to glue on the back end, and it really is just a spectacular thing. So let's adjust the brightness and contrast here, and I don't see anything. Oh, I guess I didn't check the right box. Let's try that again. There we go. Let's kind of adjust this a little bit. All right, we could actually probably, a little grainy, I think we could probably observe for a little bit longer. Let's just take a little longer of an exposure. Just the contrast. All right, tell us a little bit about Saturn, Nancy.
Well, Saturn is the second largest planet in the solar system after Jupiter. And of course, what makes it so distinct, especially in views like this, is its beautiful ring system. So right now we're looking at the north polar region of Saturn and its rings, which are fairly open now. If we get a little bit sharper atmosphere, maybe perhaps later on tonight, we might be able to see there's gaps in the ring system. So sometimes we can see this big division called the Cassini division, which is a very large gap where there's no ring material. Let's see, Saturn has a very large number of moons, like 70 something or a very large number. And it's got a lot of interesting aspects to it.
Okay, speaking of moons, let's take another picture, okay? Zach, any questions coming in?
I do have quite a few people asking to make the screen bigger, and I just notified that unfortunately, due to limitations with the software, this is as big as we can get the screen. But other than that, we've been getting quite a few good questions. As one person, when you brought this up, how are we able to see through the telescope on this computer? Why aren't we up looking through an eyepiece?
So we're not up looking through an eyepiece. We could be, but we'd have a hard time putting a camera up there that everyone could see. And actually, although it sort of can be more fun to look through an eyepiece, you can actually see quite a bit more when you use a digital camera, because what cameras have the capability of doing is exposing for a period of time. Our eyes are basically taking constant snapshots, very short little snapshots. So we can't say, all right, eye, open up and collect light, wait, and then show me everything you collected. It just takes it, it's the cadence that it takes it. But a digital camera can accumulate light over a longer period of time, which is not such a big deal for a bright object like a planet, but it is a big deal for fainter objects. So there, I blew it up a little bit. It's bigger on your screen, but now you can actually see the digital imaging nature. I don't know what you see on your guys' cameras at home, but you can see it's broken up into lots of little squares, and those are the individual elements. My guess is we probably are a little bit out of focus, and maybe we'll work on getting the focus a little bit better, but I'm gonna take another picture here. A much longer picture through a wider filter, so we're not gonna see so well the planets, but we're gonna see some other stuff. So now we're integrating for 3 seconds, collecting more light. And again, I forgot to check the right box, but here we go again.
And John, about how long is it taking the light from Saturn and Jupiter to get to our telescope?
Okay, everything is far apart in astronomy. And I think the light from Jupiter, maybe Nancy can get me wrong, we're still in the less than an hour, I think. It's kind of in the hour range, something like that. Well, this is no good. I don't see nothing in this one. All right, I'll have to try again. I guess it's not so dark out. So I think we need to stick with our narrow filter. None of this was pre-planned, folks. We're doing it all in real time. Still too bright. All right, going with a shorter exposure. Still pretty light outside. All right, so now we got our Jupiter and Saturn. Really, again, lovely, lovely picture of the conjunction there. But let's see what we can see here. What I'd like to do is to try to squeeze the contrast more to look for some fainter things. And maybe you can see, at least around Jupiter, these little pinpricks of light. What those little pinpricks are, maybe I can zoom in on them a little bit better. are, 1, 2, 3, are actually moons of Jupiter. The moons of Jupiter, there's many of them. There are 4 very large moons that have been known for a long time. In fact, ever since the first person who trained a telescope on the sky, Galileo, noticed that there were these objects that revolved around Jupiter, and they're called to this day the Galilean satellites. And there are 4 bright ones, of which I think we're just seeing 3 right now. It turns out they go in orbit, and the tilt of Jupiter's spin axis turns out to be nearly perpendicular to the plane of the solar system. So these things which look in a line, they're going around Jupiter in a way that sort of would take them out in front of the screen and then back into the screen and out in front of the screen and back into the screen. And that's why they're all found in a straight line. And again, we know well from understanding gravity and measuring these things what the orbits are. So in fact, I have a little slide, I think, here, right, that gives a diagram. This is a diagram for today of the 4 Galilean satellites. And so the one on the left there is the outermost of the Galilean satellites, called Callisto. The second one is the innermost of them, called Io, a spectacular place that has volcanoes. Ganymede is just hitting the disk of Jupiter, so we can't see it because it's right in front of Jupiter. And Europa is the one to the right of Jupiter. And Europa, something interesting about Europa, Nancy?
Indeed, there is. Europa is an icy moon, and it's believed to have a salty liquid ocean underneath its icy crust. And so it's a tantalizing place to go if we're interested in looking for places where we might try to find life in our solar system.
All right. Under ice swimming right there. Let's see. I'm not sure. The moons of Saturn are quite a bit fainter than the moons of Jupiter, so we need to expose for a little bit longer, but the sky is a little bit too bright for us right now to expose a little bit longer, but it's probably getting darker by the minute. So let's see if we can go up to Saturn. There's Saturn up there, and I don't see much in the way of moons, but let's see how long we can go. We can at least go, I'll bet we can go 3 seconds now. Let's see. It's probably going to take a few more minutes before we're going to be able to see the moons of Saturn for it to get dark enough out, but let's just try this one.
While we're waiting, I got a good question about the moons. Do the moons of Jupiter and Saturn have a gravitational pull on their respective planets the same way our moon kind of has a gravitational pull with the tides?
In fact, it does. Actually, a kind of more dramatic thing is, although the moon affects us with its tidal forces, the Earth affects the moon with its tidal forces. And that's a big deal around Jupiter, because Jupiter is such a massive planet that the tides it has on the moons are so extreme that it actually heats the inner parts of the moons. And that is why the inner moon Io has volcanoes, even though it's way far away from the sun. It should be freezing cold out there. That was a surprise when the Voyager missions flew by and they saw that. And then people thought about it and realized it made sense. And that is why there might be liquid water under the surface on Europa, because there's some heating coming from the tides of Jupiter. Did I get that right, Nancy?
You did. And it's even more complicated because the moons pull on each other when they line up in a row along their orbits around Jupiter. So when they're in a perfect position, sometimes Io is being pulled on by Jupiter to its inside and Europa to its outside. So it has even more of an effect.
All right. I think that we're probably going to have a hard time seeing the moons of Saturn for a few more minutes, but we can open it up for more questions if people have any.
Yes, John. So I do have a few more questions. I've been getting quite a few questions with how far are Saturn and Jupiter physically apart? And for today, how far apart are they in the sky? So what's the distance between these planets?
Okay, that's great. I almost decided to write a trivia question and do that as a Zoom polling question, but I didn't quite do it. But I do know the answer to it. I think they're physically in space about 500 million miles apart. So that's quite a long ways from each other. So they look like they're in the same direction. Again, we should just be keeping this one up here while we're doing that, because that's what we're here for, is this conjunction. They look like they're close together, but they're physically far apart. Now, when we say they're close together in the sky, we measure that distance by an angle that they are apart. And maybe people are familiar with the idea of 360 degrees in a full circle. And so right now, these two planets are about 1/10 of a degree apart angularly. So that's for direction, but physically in space, they're very far apart because Saturn, of course, is much further away from us than Jupiter is.
It's actually twice as far from us in general as Jupiter.
What else do you got, Zach?
Yes. So how do we talked about the moons affecting the planet? Someone wanted to know if the moons of Saturn are affecting Saturn's rings and how that might affect what we see with the ring structure.
So that's a spectacular question, which I'd love to answer, but I'll let Nancy answer it.
I'll start and then you can finish. So indeed, Saturn's moons do affect Saturn's ring system. In particular, so Saturn has a few different classes of rings. There's one of moons. There's one in particular that's quite large called Titan. Then there's a handful of others that would be considered medium size. And then there's dozens and dozens of little tiny moons. And some of those little tiny moons are actually embedded within the ring system. And so their gravity actually has helped to shape the rings. And in some cases, it can form clearings or gaps within the rings. So the moons play a really important role in the long-term stability and evolution of Saturn's ring system.
And I encourage you, if you're interested in that, there are some just phenomenal pictures of the things that gravity does to the rings. And in fact, the Voyager flyby measured a lot of those things. And sitting in a room in a closet just down the hall from here is a bunch of spools of film, of Voyager film. And I want to pull them out and find some that have some rings and put them up on the wall. Those things have all been digitized now, but we actually have a copy of some of the film from Voyager. I was hoping maybe we'd be doing better at seeing some moons of Saturn, but it's still pretty tough. Pretty tough. Maybe a little moon right up there. Let me get my cheat sheet on Saturn. And sure enough, there's Saturn. And these are the smaller moons. The biggest moon of Saturn is Titan. And that's the one that Nancy was telling you about. And I'm pretty sure that little speck is it. Should we zoom in and try to get a little better picture of it? Let's do that. I have one way of doing it.
And while you're doing that, I just got a question about, could Saturn and Jupiter ever possibly collide with each other?
So collide with each other in space? No. But I was looking this up. Could we ever get a conjunction? I know one thing you might have been hoping for, where they were like right next to one another. And it will happen sometime, but I tried to look it up, and I think the time scale for when that might happen is probably hundreds of thousands of years. But again, it's hard to predict because we know it orbits very accurately, but not that accurately, for hundreds of thousands of years out. But even when they appear in that same direction, they'd still be quite a long distance apart. So no, I think the answer is no, they're not gonna collide. However, there might be things, there's little objects in the solar system, asteroids and comets, which go on orbits that sometimes cross the orbits of planets. And sometimes they do collide in planets. And I'm not going to take away Nancy's slide that's coming up here that shows such an event that happened in the mid-90s. And in fact, and Nancy will correct me if I'm wrong here, it's possible that a satellite, that an asteroid or comet came close to Saturn, broke up from the tides of Saturn, and may have been responsible for populating some of the rings that we see today. The rings may not have always been there, and they may have resulted from something like a near collision or a collision. Okay. Other questions?
So yes, we have these pictures right here, and we're getting great quality pictures, but we have some people asking, how would we get better quality or better resolution, or what's affecting the resolution and quality of these images that we're seeing tonight?
Okay, so the sharpness and the ability to see detail is limited to some large extent by the Earth's atmosphere, the turbulence in the Earth's atmosphere. And sometimes it's better and sometimes it's worse. So sometimes you can get sharper pictures. And sometimes you can take, if you take lots and lots and lots of pictures, sometimes you get lucky and see good ones. And so, so sometimes you might see some pictures that have come out of ground-based observatories that have considerably more detail than these. And we may try to get a high-speed camera someday to do imaging like that. But the very sharpest images that you see, and Nancy will have some in her presentation, which we should get to shortly here, are taken from either telescopes in orbit around the Earth, like the Hubble Space Telescope, or the even sharpest pictures. You get a sharper picture if you get close. And we've sent several spacecraft, both for flyby missions past the giant planets and actually orbiting missions that stay there for many years and take many pictures. And Nancy will show you some slides of some of those. Okay, I think we should switch over to Nancy's presentation, unless there's any great last-minute questions. I didn't seem to get a great picture of Titan here. I don't even know what I got a picture of.
One last question. So we looked at the simulation of the planets. We looked at Jupiter's moons. We looked at Saturn's moons. And every time we looked at them, we see that all the orbits were flat or in line with each other. How come that is?
Well, so it's actually interesting. If you look in this diagram, which is not a real picture, in Jupiter, they're in line with each other because the rotation axis is perpendicular to the plane of the solar system. So like I was saying, these orbits don't go around the planet like this. They kind of come out of the page and then into the page and out of the page. But Saturn, the rotation axis is tilted a little bit. That's why we see the rings opened up, as Nancy said. And the orbits of the moons, you can actually see on the plane of the sky. So if you were to look at Titan would make an orbit that would look something like this. In a few weeks, I think it takes to make about one orbit of Titan. Okay, Nancy, you want to tell us a little bit about research on the gas giants? Hey, before you start, I just have to let everyone know, in case you can't see it, we have 325 people on this call, which is really cool and amazing. And we're gonna be doing this again, which I'll tell you about a little bit after Nancy finishes her talk.
And to interject, we have over 200 people on Facebook. So in total, we have over 500. Thank you all for showing up.
Yeah, thanks.
All right, so I wanted to take this opportunity to tell you a little bit about the sort of legacy that we've had at New Mexico State University in terms of studying the gas giant planets. And I'm really mostly talking about Jupiter and Saturn here. I'm going to focus a little bit on Jupiter, but I really mean Jupiter and Saturn. But we've had a sort of a long history of studying these planets, so I wanted to sort of share with you that journey. Next, please. So I'll just briefly tell you a little bit about why Jupiter and Saturn are interesting to astronomers, why we want to study them, why we send spacecraft there. I'll talk a little bit then about that connection with NMSU's astronomy department and the role that we've played over the last 50 years. And then I'll end with a few thoughts on sort of where we might be going, what directions we might be taking. So in terms of why Jupiter and Saturn, or the gas giants in general, are interesting, we think that the solar system, or planetary systems in general, formed out of gas clouds, clouds of gas and dust that were spinning, and out of those clouds of gas and dust, the planets formed. And that's sort of shown in artist rendition on the left there. And so, in order to try to understand how we went from a picture like that to what we see today, which is a bunch of planets with not much in between, we really need to understand the composition and the sort of design of the giant planets. They tell us a lot about what materials were in the early solar system and how those have formed to shape the giant planets. Because the giant planets are so large, they actually have a substantial amount of gravity associated with them, as you heard about from John earlier. Jupiter itself Jupiter and Saturn combined are like 90% of the mass of all the planets in the solar system. So they're really very massive. And what that means is that they actually influence through their gravity, not just the moons around them and their local environment, but also any object that happens to come by and make a close approach. And so an example of that is shown on the bottom there, where you see a series, this is again an artist rendition, although I'll show some real images in a second, where a comet passed very close to Jupiter, and Jupiter's gravity, number one, tore it apart into like 22 fragments, and then each of those fragments impacted Jupiter. But it has a large influence in terms of its gravity and things moving around the solar system over millions of years. And then lastly, the giant planets serve as a natural laboratory for helping us to understand some really basic fundamental physical processes that we see in the universe and also just here on Earth. So the image sort of centered in your screen is a recent image of Jupiter taken by the Juno spacecraft. And what you see there is actually a view of Jupiter's poles, which is kind of difficult to do from Earth. But you see all these swirly clouds and different bands and colors, and it's a false colored image, but still you see all these beautiful swirly clouds. And so it's like a giant fluid laboratory that helps us better understand how gases move and how fluids operate even on our own planet. And then the image in the upper right is a composite image of two different types of images taken by the Hubble Space Telescope. You see the main image is a color image of Jupiter. And then at the top there, you see some glowing gases near Jupiter's North Pole. And those are gases that are emitting light because charged particles from the sun are interacting with Jupiter's magnetic field, creating aurora, just like the northern and southern lights we have here on Earth. So they're really a great laboratory for studying those fundamental physical processes. Next, please. So as you've already heard a little bit about tonight, NMSU has had a long, rich history in studying the giant planets. And I think that's really because we sort of had all the right ingredients over a long period of time. Number one, we had a telescope that we could designate for really long-term monitoring studies of the planets. It wasn't a telescope that was used for, looking at stars and galaxies and planets, just the planets. And that's the telescope that you've seen tonight that John showed you with the video. We also had and continue to have faculty and graduate students who have expertise and interest in studying the giant planets. So that's also a good thing if you're trying to do it over a long period of time. And then, as we've already talked about earlier tonight, we're located in an environment where we have many clear nights a year, and that has enabled sort of these long-term monitoring studies where we can really see how Jupiter's atmosphere changes over periods of weeks, months, years. All right, so speaking of the long-term monitoring project, this was already, again, touched on by John, but I wanted to just sort of talk you through kind of that history. This was a project that was led by Rita Beebe, and it was funded by NASA for many decades over the time periods when we had NASA had spacecraft that were either flying by or orbiting the giant planets. In addition, so you see in the bottom left, Rita Beebe getting an Exceptional Achievement Award from the NASA Associate Administrator, who's shown on the right there, Thomas Zurbuchen. That was just last year. So, she's made sort of decades and decades of really vital contributions to the studies of the giant planets. What you see in the middle there is our dedicated observer, Scott Murrell, and one of Rita's former graduate students, David Keene, who worked together to get that orange can that you see behind Scott's head operating on the telescope. And so, again, the telescope started out with photographic plates that were used to collect the observations, and then we transitioned to this digital camera, one of the first of its kind in 1989. So these observations have provided a long-term record of the giant planet atmospheres throughout the Voyager missions and further on, and I'll talk about those in a moment. Next, please. Okay, so this is again trying to show how we're going from using photographic plates, which are shown on the left. So in that person's hand is a photographic plate, and that particular image is one of the moon, but you can sort of see what that looks like if you were to hold one in your hand. And the types of images that it produced are shown on the bottom two panels of Saturn and Jupiter. And then we transitioned, as I said, in 1989 to using a digital camera, which uses a silicon chip, like what you see in that person's fingers, to take images like the ones you see on the right-hand side. And those are 3 images of Jupiter taken in the mid-1990s with that digital camera in the orange canister that you saw. All right, so why do we care about studying Jupiter and Saturn or monitoring them, as I said, over long periods of time? Because it enables us to, number one, look for serendipitous discoveries. So on the left-hand set of images, you see on the very left image is an image taken from the Tortugas Mt Observatory. It was a night that we were just taking Saturn routinely, and it just so happened that there was a giant storm that erupted in Saturn's atmosphere, which we saw with our telescope here, and then was followed up with Hubble Space Telescope, shortly after Hubble was launched, in fact. And so that's the image that shows the great, sort of the ribbon structure of that storm taken with Hubble Space Telescope. Another thing that long-term monitoring provides you with is the ability to detect changes over long periods of time. And so what you see on the right is a series of images of Jupiter's Great Red Spot. These are images that were actually taken through a combination of spacecraft observations, but I show them to illustrate to you how the Great Red Spot has changed over the last several decades. So if you look on the bottom left, that's the extent of the Great Red Spot when Voyager went by in 1979. And then if you look on the top row, you see what the Great Red Spot looked like, just a few years ago. And it's not as oval, it's much more round, it's much smaller, it's gotten darker. So it's really undergone many significant changes. It's hard to get time on spacecraft like Hubble Space Telescope. So we might be able to look at Jupiter with Hubble once a year, but we can look at Jupiter from the ground, once a day, weather permitting, for some periods of months. And so that allows us to look for long-term changes. Next, please. So I wanted to sort of show you some examples of the types of observations that investigators from New Mexico State University have acquired from spacecraft, from Hubble first, and then from orbiting spacecraft. So these are a set of images taken by the Hubble Space Telescope through various programs, again, that Dr. Beebe was the PI on, or the principal investigator. On the left, you see Saturn, and that's actually an example of a different storm that erupted in Saturn's atmosphere in 1995. So the big one that you saw on the previous slide was from 1990. This one was, and they said, oh, those usually come every 30 years. And then there was another one in 1995. So Hubble was put right on it, and we got some really good observations of that. In the middle, you see a color image of Jupiter taken with Hubble Space Telescope. And as John said, these pictures are much more sharp, and we're able to, make these really detailed observations because we're above the Earth's atmosphere with Hubble. And so we don't have to contend with the blurring effect that the atmosphere causes. And then in the upper right, we have an image of Jupiter taken in the infrared with Hubble Space Telescope. So this is a different kind of light, but the reason why this is important is because the infrared light is sensitive to kind of different cloud layers within Saturn's atmosphere, Jupiter's atmosphere. And so by studying Jupiter in the infrared, that allows us to probe different altitudes in the atmosphere to understand the clouds at different layers or different depths. Next, please. Okay, and as John alluded to, in the mid to late 1990s, we transitioned a little bit from making our dedicated observations with the Tortugas Mountain Observatory to studying Jupiter using the 3.5 meter observatory at telescope at Apache Point Observatory. So these are a couple of examples of Jupiter observations from investigators at NMSU over the years. So in the upper right, you see an image of Jupiter shortly after the telescope opened for business. It was like within a month or two of the telescope's commissioning. And you can see these were images. This was an image taken when those comet fragments impacted Jupiter's atmosphere, as I talked about earlier. And so you see the Great Red Spot is that bright oval, it's sort of in the middle, and then the three lower spots are different comet fragments that impacted Jupiter's atmosphere. More recently, we've continued to study Jupiter's atmosphere using a different kind of instrument, and these are three of like 250 different colors of Jupiter images that we've acquired over the course of the Juno mission, which is currently in orbit around Jupiter. And I'll say a few more words about that in a moment.
I'm just going to break in here for one moment to say that our own Nancy Chanover is the director of the 3.5 meter telescope. So.
Yeah, so if I had my way, we'd study Jupiter all the time, but it's used for lots of exciting science. So lastly, we've had a number of, NMSU's been involved in some of the missions to the outer solar system, not just the ground-based observations. So I wanted to touch on that briefly. On the left there, you see a color image of Jupiter taken by the Cassini spacecraft. Now, Cassini was actually sent to orbit Saturn, but it happened to pass by Jupiter on its way. It wasn't a coincidence, it was intentional. But as it passed by Jupiter, it collected some really important observations of Jupiter's atmosphere. So that's an example of one shown there. On the upper middle, you see a false color image of Jupiter's Great Red Spot that was made with several different images from the Galileo spacecraft. And so you can see that by getting up close and personal with the planets, it provides you with detail that you just can't get from Earth. And so this is an example where you could actually, or we could actually track the motions of the tiny little clouds inside the Great Red Spot to try to understand the winds within that storm, sort of like we would study the winds inside a hurricane on Earth. And then lastly, on the bottom there, you see a different image from the Juno spacecraft, which is currently in orbit around Jupiter. Juno is making a bunch of different kinds of unique observations that have never been made before. One of which is that for the first time, we've been able to take these really sharp pictures of Jupiter's polar regions. Normally, spacecraft go around the planets near their equators. Juno is going up over one pole and down over the other. And so this has provided us with unprecedented views of the polar regions of Jupiter, which are an important region of study for us in the astronomy department. Okay, next, please. Yeah, so I wanted to say a few words about some of the projects that we have going on at the moment. We've got a few different grants and graduate student fellowships actually funded by NASA to study different aspects of Jupiter's atmosphere, how the clouds change with depth, how the swirling storms near the poles, which you see in that infrared image from Juno in the middle there, how those swirling storms interact with each other. And so that's been a really exciting, and how Jupiter's interior behaves. And so those are several different grants. On the left, you see Vladimir Lira, a faculty member. You see Ali Haider, who's a graduate student working with Ali and working with Vlad and me. In the middle there, you see Jason Jakowitz, who studies primarily the interior and behavior of Jupiter's inside. You see our colleague, Dr. David Voles from the Department of Electrical and Computer Engineering. He's been involved with projects both with me and with Jason Jakowitz. And then you see one of our graduate students, Emma Dahl, who's been studying the clouds of Jupiter and their colors. Okay, next. So where does this lead us in the future? There's a bunch of different areas of direction that I think we're going to be taking our studies of the giant planet atmospheres. And here's a couple of examples. So on the left, you see an actual image of Jupiter, and you see it kind of in a crescent mode. We don't ever get to see it that way from Earth, and it requires a spacecraft to be in the right position to be able to image Jupiter that way. But the reason that's important is because, as John alluded to a few moments ago, we're starting to a lot more people are starting to study planets around other stars. And the bottom there, you see a cartoon of a planet that's orbiting its star. And from Earth, we see this thing called a transit, where the planet passes in front of the star and blocks out a little bit of light. But you can see that you also see that planet in these different like crescent phases, right? And we don't get that view from Earth. And so it's really important for us to try to study that using Jupiter basically as a proxy for what we think these planets around other stars should be doing or should look like. And then lastly, on the right, that's an artist's rendition. So that's not an actual image, but that's an artist's rendition of a planet around another star that was directly imaged. So normally we detect planets around other stars by sort of measuring their influence on the star. It's really difficult to actually see the planet itself, but there's been a few cases where that's been possible. And one of our new faculty members, Eric Nielsen, his research is really pioneering in that area. So we're excited about trying to learn more about directly imaged Jupiter-like planets around other stars. Okay, so in summary, we've had 5 decades or so of really exciting research at New Mexico State involving studies of the planets. We've got 5 former and current faculty members who have worked in this area. It's produced at least 16 PhD dissertations and 2 master's theses, and we've been really successful with getting support for our research from NASA and the National Science Foundation. A lot of these efforts have really provided us with opportunities to study how these giant planets vary over time. And that's been a really important contribution to the field. And, I think for the future, there's a lot of interesting directions that we're going to take it, and we're excited for what the future holds. So thanks. I'd be happy to take questions.
Yes, I do have a couple questions for Nancy. Someone asked if you could elaborate exactly what is the Great Red Spot on Jupiter, and when we looked at Saturn, we saw some other spots that looked the same. So could you elaborate a little bit more on what exactly that is?
Sure, I'd be happy to. So the Great Red Spot on Jupiter, it's sort of the best analogy I could think of is kind of like a hurricane on the Earth. The important difference, though, so it's a cyclonic, it's a circulating storm system. Hurricanes on Earth, you probably know, form over the oceans, and then once they encounter land, it of course has devastating effects for populated areas. But after that encounter with land, the storms tend to lose energy and they sort of peter out. Jupiter doesn't have that problem because there's no land for it to encounter. So the storms sort of continue in their cyclonic behavior. They're sustained over hundreds and hundreds of years. So they are basically cyclonic or circulating storm systems. One of the areas of study in our department is what makes Jupiter's red spot red specifically. And that's, believe it or not, something that's not very well understood. But we've got some good hints that it might be some sort of hydrocarbon molecules that are being irradiated by sunlight. And then the storm on Saturn was kind of a different sort of thing. That was more like a convective bubble, sort of like a dear friend who will remain nameless calls it a big burp. So it's like a burp of gas from Saturn that sort of punched up into the upper atmosphere. And it was this, sort of fresh white material. And then over days and weeks, that material gets sort of spread out into the atmosphere. So it's not sustained like an organized cyclonic storm system.
Gotcha. Thank you, Nancy. Also, what have we learned from other wavelengths like X-ray, radio? So we're looking at Jupiter and Saturn through the visual right now, but what have we learned about these planets, specifically Jupiter, from the other wavelengths?
That's a great question. So I'll give you a sampling of an answer, but it's certainly not going to be complete. So for example, in the ultraviolet, that's where we're sensitive to those auroral emissions that you saw of that sort of ring of glowing gas near Jupiter's polar regions. So we've been able to study the aurora on the giant planets using ultraviolet light. The infrared light, depending on what kind of infrared or what wavelength, that's really sensitive to different, the fingerprints of very specific molecules in Jupiter and Saturn's atmosphere. So the infrared light is a great way for us to study really the chemical composition. And it tells us that Jupiter has exotic molecules like phosphine and ammonia and all kinds of interesting hydrocarbons. Let's see, in the radio, we can actually study the magnetic signature of Jupiter and how that behaves as Jupiter rotates. So really, each wavelength region probes different physical processes, and they all sort of come together to sort of give us a more complete view of our understanding of the giant planets. Looks like John's got another picture for us.
There we go. The Great Conjunction. It kind of changing the contrast back and forth to see stuff on Jupiter.
Yeah.
And then to see Saturn well. So let's see, Zach, any more, just one or two more last questions, if you got anything?
Just one more to clear it up. Nancy, on one of your slides, it said false color. What exactly do you mean by false color images?
Great question.
That is a great question. So, when our eyes see color, we're actually sensitive to different colors of light, and all of those things are sort of combined into a single image in our brain. When we take pictures with a telescope, for example, as John mentioned at the beginning, we actually are filtering out all the other light except a pretty specific color that we're interested in. So I might take a picture of Jupiter in a very specific color of violet and a very specific color of green and a very specific color of red. And then if I want to sort of visualize what that looks like in a color image, digitally, I can combine each of those three individual images and assign them to be a different color on the computer, and that's what makes a color image.
Okay, any other great questions, Zach, or should we call it a wrap?
I think people are just curious to see that you already have it on the screen. But I think a lot of people are wondering, I know we talked about this a little bit, but if we're about to close out. So what do they need to do to step outside, see this? How long will this happen? And how much longer do they have to see this in the night sky?
So if you step outside right now, it'd be good to go look in the southwest and test your eyesight by seeing whether you can separate Jupiter and Saturn, or if you have a pair of binoculars, pick up a pair of binoculars and take a look at them. And over the next several weeks, Jupiter and Saturn will just be getting gradually further apart. This is not some dramatic thing where they were way apart and then one night they're right together and then they'll be way apart again. It was gradually coming together and it'll be gradually going apart. But the thing that'll limit you from looking at Jupiter and Saturn for too much longer is they're pretty low in the west, which means they're going to set below the horizon because they set because the same way the sun sets because the Earth rotates. And in really just a few more weeks, there's not going to be much window after sunset when you'll be able to see Jupiter and Saturn. So yeah, goodbye for a few more months till we come around in orbit and get to see them again, at which point they won't be in the same direction. So I encourage you to go out and take a look. And let's see, let's just close this out by first of all saying thanks. One thing that I'm going to try to do is I'm going to try to take some of the photos that we made today and make maybe a couple screen grabs or little images of them, and I will email them around to the mailing list because I have many of your emails if you sent requests for passwords. So I'll take advantage of those and maybe send you a photo that you can have as a keepsake. And if anyone cares to send me another email with a physical address, we have bumper stickers, Friends of Tortugas Mountain Observatory, which I'd be happy to stick in the mail for you if you think that'd be fun. And I think we had a lot of fun with this event. Hopefully you guys had fun. And I think we're going to plan on doing something like this on a regular basis. We usually have a monthly open house at our campus observatory, but we can't do that during COVID. So I think maybe this spring we're going to try to do this every month or so, and maybe we'll do that even when we can do campus observatory. And we kind of like this idea of just kind of concentrating on looking at one thing and talking about it in a little depth, and spreading out the wealth. There aren't that many things to see with a small telescope. Well, there's a number, and we'll spread them out over a number of months. And hopefully I can take advantage of this email list that I have and inform you of those things. If you get emails from that and don't want them anymore, just send me an email saying, take me off that list, and I'd be happy to do that. And with that, I'll turn to Nancy and Zach to see if they want to say anything. Zach gave a big thumbs up. Any parting words, Nancy?
I just would like to say how thrilled I am to see so many of you here tonight. You know, I've seen a lot of names on the participant list. Many of you are friends and colleagues, and some of you are new to us, and we're just delighted that we were able to share this with you tonight. So thank you so much for coming, and I hope we get to do it again soon.
I'm also very excited. I've wanted to do this for a decade, 2 decades. Yeah. We got there. Okay, we're gonna close this out. Thanks again, everyone. Have a great evening and happy holidays.